The recording is live. All right. Welcome everyone to yet another day of Chemistry 1A. Today we are starting a new topic titled the periodic table. Everyone should have received, I should have just handed out a single sheet, single copy of a periodic table to every person. We will talk about specifics about it as we come up. I'm just handing it out in advance right now. Just as a reminder, today is Wednesday. The next time we see each other is Monday. Monday is the day of our first lab, our first wet lab. So please don't forget, if you haven't already, to number one, sign and upload those safety agreements. And number two, complete the safety quiz in preparation for Monday's lab. If you don't complete these, either of these or both, you will not be permitted to join the lab until you do. If you don't do it at all, of course, that day will be, of course, counted as an absent. And for those who may have forgotten, 3 or more absences in lab is an automatic failure of the course as a whole. All right. So we do want to ensure that we're not taking up that 3 misses too early on. Before we get into today's topic, just a quick little recap of what we covered on Monday. On Monday, we continued our historical conversation of chemistry as a whole. We talked about what atoms and molecules were made of. Back in the fifth BC, 5 BC, they described it as atomos. These were invisible particles. Aristotle, a philosopher, had the idea that there were 4 primary elements: fire, earth, air, and water. It wasn't until we eventually get to 1807 that John Dalton was able to devise his atomic theory. Now, remember, the idea behind a theory is that there is substantial evidence, but not comprehensive. In other words, Dalton's atomic theory was pretty damn good, but it wasn't perfect. Take a handle, take a handle, take a handle. But it wasn't perfect. A lot of these guiding principles inform us even today, but we have to accept the possibility that his theory wasn't perfect in certain cases. Dalton's atomic theories are as follows. Number one, matter is comprised of extremely small particles called atoms. Number two, each element has only one type of atom. So, for example, a copper penny will only consist of copper atoms. Number three, atoms of different elements have different properties, aka every element is unique. Number four, handout, handout, handout. Number four, compounds contain atoms in whole number ratios. For example, water is H2O. This implies a 2-to-1 relationship. You're never going to see something like H.5 O3.7. Decimals will just not be seen here. Compounds will be in whole number ratios. And then finally, number five, atoms are conserved in reactions. This actually comes back to one of the fundamental laws of physics. Matter can neither be created nor destroyed, only transformed. In the example we showed here with just using green and red circles, we see that on the left-hand side, we have 4 green circles, 2 red. Although there has been some rearrangement, the number of red and green has stayed the same, so atoms are conserved in reactions. That's what then led to our discussion of how atomic theory has evolved since John Dalton. Over the next few decades, almost a century, we had various ideas. In 1897, Thomson discovered electrons. He described them as being negatively charged and found everywhere, aka omnipresent. In 1909, just less than 15 years later, a physicist, Millikan, confirmed that the electron was negatively charged. Remember, we talked about this being a theory. There was substantial evidence, but not comprehensive. So even though it already existed, Millikan confirming the existence of the negative charge was instrumental of itself. Just a few years later, Rutherford discovered alpha particles. Alpha particles are positively charged. His experiment was actually really, really cool. Just using a gold foil, using an electron ray gun, he quite literally would shoot electrons and alpha particles through the gold foil. In this process, he noticed something. He noticed that when the electrons hit the gold foil, the particles hit the gold foil, a couple things happened. Sometimes they went straight through, no change in speed, direction, or whatever. Sometimes they would change direction and speed just very slightly. And then sometimes they would actually just get bounced right back. So 3 different big types. All of this together led to Rutherford's big conclusions. Number 1, atoms are mostly empty space. That accounts for some of those particles getting shot straight through with no change in speed or direction. Number 2, there is a dense positive nucleus at the center of these atoms. Right, electrons are positively charged, so electrons would favor those nuclei. Alpha particles would be repelled, and then finally, the nucleus is very small. These guiding principles still light our day to today, and it is, of course, what led us to understanding the structure of an atom consisting of 3 fundamental particles. We have number 1, an electron, number 2, a neutron, number 3, a proton. If we think of an atom as similar to a planet or even a Ferrero Rocher, inside the nucleus, inside that gooey chocolate center, you will have your neutron and proton. A neutron, as the name suggests, is neutral. It has a charge of 0. And a proton is positive 1. So that gooey chocolate center of the Ferrero Rocher is overall positively charged. Outside of the nucleus, outside of the Ferrero Rocher center, you have that crispy hard shell. This is where the electrons are found. The best analogy for this is a planet. The planet has rings that surround, that orbit the planet. Electrons are found on those rings. Electrons carry a charge of -1. Now, we can describe the mass of these chemicals in 2 forms. We can describe them in our standard SI unit, grams. However, the limitation of using SI is that these particles are incredibly small. Looking at the exponents, we're up to -28. That's a lot of zeros. As a result, it becomes very difficult to understand these masses on this scale, be able to talk about them qualitatively. So we use what is known as AMU, atomic mass units. They're just a slight conversion. We see here a much more organized display of masses. We see here that number 1, both neutrons and protons have similar but not identical masses. If you did it solely based on the grams, you would think they were identical. And the electron, much smaller than the neutron and proton, is a lot lighter. While, of course, you are able to make that same conclusion with the grams, again, we talk about that laziness factor. It's just a lot easier to describe these things in terms of AMU. The relationships that we're going to see here today are from Monday's class. Atomic number, Z. The atomic number tells us the number of protons. It also tells us the number of electrons. When both of these are equal, when we have a same number of positive and negative, this is a neutral atom. It's overall not charged. To determine the mass of an element, aka A, it is the mass of the protons added to the mass of the neutrons. But how do we get the number of neutrons? That's just the atomic number A minus the mass Z. The most generic way we will see this represented is in the form AZX to the N, where X is the symbol of the element, A is the mass, Z is the atomic number, and occasionally you will have a charge. Traditionally, it'll be absent, aka the element is neutral, but it is possible to see it there. We did a couple examples just showing them right here. Back on Monday, we did not know what Mg and Ca meant. Today we will. But back on Monday, we were able to determine from the symbol, this mass is 24. The atomic number is 12. The symbol is Mg. And since the charge is left blank, it is assumed to have a charge of 0. The same thing can be said for this molecule over here on the right, the Ca. Same idea. Mass is 40, number is 20, symbol is Ca. Here we have a situation where we do have a charge, 2 plus. It can be written +2 or 2 plus. They mean the same thing to me. We do have to include the charge, meaning if it is a negative, we have to write the negative symbol. We then talked about isotopes, how there were atoms of the same element with a different number of neutrons. We had, for example, carbon-12 and carbon-14. Carbon-14 is most commonly used in dating radioactive isotopes, historical artifacts, and the like. We see here in the case of carbon-12 and 14, they differ in terms of their mass. Handout. And by differing in terms of their mass, they differ in terms of their neutron. We apply that same logic to another element, hydrogen. Hydrogen, one of the most notable examples throughout history, the hydrogen bomb, has 2 more isotopes, deuterium and tritium. In theory, they could also supply a source of energy, but after learning from the hydrogen bomb, I don't think anyone's going to try it. But the idea, of course, here is set. Every element will have some variation of isotopes that only differ in terms of their mass and neutrons. So how do we know what the standard is? How do we know what the normal is? How do we know if we're going to see carbon-12 or carbon-14? That led us to atomic mass calculations. Atomic mass calculations can be seen as the sum of the abundance of that element times its isotopic mass. Now, this fractional abundance is generally referred to as how much it exists in the world. One of the questions we did was calculate the average mass of boron given boron 10. Why did I call it boron 10? Because it's labeled 10. It has an approximately 20% abundance with an atomic mass unit of 10.01. Boron 11 has an 80% abundance with a mass of around 11.00. We simply multiply the percentages by the masses and we sum them together. We're able to get the average mass. Following our significant figures rules, we expect the average mass of boron to be around 10.9. And that is, of course, what leads us into today's conversation, the periodic table. We are still in chapter 2. Now, the periodic table in its current form was devised by a man named Dmitri Mendeleev. And this was in the mid-1800s. Dmitri posited the idea of a table that organized elements based on mass and chemical properties. Let me just write generically properties. AKA, Dimitri's big idea was, well, if these 5 elements all are blue, then maybe they should be in the same group. If these 10 elements all have similar masses, maybe they should be in their own group. But Dimitri's idea was simply an idea. It was a table that organized elements based on their mass and properties. And this was in the mid-1800s. So if you actually remember historically, Dalton did his thing. Dalton did his thing in 1807. And it wasn't until the 1900s, Rutherford and his other contemporaries, handout. Yep. It wasn't until the 1900s that other scientists continued to organize or contribute information. So was Dimitri's idea perfect on first go? No, it was not. But he had the first idea to organize elements based off of mass and properties. It in fact wasn't until the early 1900s, a guy by the name of Henry Moseley, this was in 1913, Henry was the guy who actually coined the term atomic number. A concept we saw on Monday, atomic number. As a reminder, the atomic number tells us the number of electrons and protons present together, or not necessarily, you know, they're not nearly in the same room, but taking the information that Dmitri had started, taking what his contemporaries had contributed, taking what his colleagues had contributed in the early 1900s, Henry Moseley was able to devise the periodic table. Where does that word come from, periodic? In the context of the table, as well as chemistry, it came from the term periodicity. Periodicity is the idea or phenomenon seen when both chemical and physical properties share a pattern. In a periodic way. This is what gives rise to the periodic table. Now, at this point, every person should have their own copy of the periodic table. I'm going to make one thing clear. This is the periodic table we will be referring to throughout this course, throughout your exams. This is the ACS, American Chemical Society. This is the Nationalized Society official periodic table. There are variations online that slightly differ in terms of color, maybe in terms of decimal places. So for example, on the handout in front of you, if we zoom in to that PT at the very top, you'll notice that for this case, they put the atomic number on top and the average atomic mass on the bottom, and they only go to one decimal place, or at least in, well, two decimal places on the actual table. So I want to make it clear that other versions online just might be slightly different aesthetically, but this is the document we will be referring to. This is a document I will be giving you as part of your exam, right? So this is the periodic table I expect you to continually carry to class, that I will be continually referring to, or anything else on this. Now, for the next few minutes, we're going to talk about the periodic table. We're going to talk about some details and some trends. So while I encourage you to write on the paper, just know that you'll be writing a lot. So you may want to write on the back of the sheet or on your notebook. Okay. Looking at the periodic table, we notice a couple things. Now, before I go any further, I actually want to make something clear. There are these two bottom rows right here that start with LA and AC. I'm going to put this right now. We will not encounter these guys in Chem 1A. These guys are a bit too complicated for us to really talk about their chemistry. This is something more apropos to an advanced course, not for general chemistry. So what I'm trying to say to that is we're just going to zoom in on that middle section, and that middle section only is where we're going to focus on. All right. First thing I want us to notice is that there are labels on top of each column. We see 1, 2, 3, 4, 5, 6, 7, 8, all the way to 18. the columns are referred to as groups. So for example, we would say Mg is found in group 2. We would say that Cr is found in group 6. We would say that F is found in group 17. The rows are named period. So for example, magnesium is in group 2, period 3. Cr is in group 6, period 4. F is in group 17, period 2. I expect you to be able to know / memorize the first 20 elements. So that starts off at this H right here and actually stops at Ca down here. So it's this entire couple rows. When I say I expect you to know / memorize, I'm not going to say on an exam, hey, what's element 17? No. I could say, hey, for nitrogen, aka N, what atomic number is it? What group is it in? What period is it in? What's its mass? The first 20 elements are the ones we will most frequently encounter. So by the time the semester is over, you'll probably have you'll already have them memorized in some way, shape, or form. Please note that the names are provided in each cell. So H is hydrogen, Be is beryllium, Mg is magnesium, He is helium, and all that stuff. There is a periodic table song that might help you with your memorization. I think the official song is in alphabetical order, so it's not really apropos to right now, but it goes in tunes of 4. So 1, 2, 3, 4, 1, 2, 3, 4, and so forth. The song would go hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, and so forth in repeating groups of 4. So the sing-song effort might help you just at least memorize them, but it's not the only way to memorize it. So what does this table tell us about Mendelev's original idea of organizing them based off of mass and properties, and Moseley's idea of atomic number? Well, one of the first things you should immediately notice on the periodic table is it's sorted, or rather organized, in terms of atomic number. Chromium is number 24, manganese is number 25, cobalt is number 27, and so forth. So the periodic table is organized in terms of protons and electrons. Hydrogen has only 1 proton, 1 electron. It's at the very, very front. At the very, very end, Og, oganesson, has a mass of 294 and an atomic number of 118. What does that mean? It means it has 118 protons and neutrons. All right. What else can we glean from this table based off of what we know about Moseley and Mendeleev? Well, remember, the idea was that they organized it in terms of overlapping properties. So looking at the color code right here, we're looking at the very top left. It says alkali metals. Alkali metals are in yellow. You'll notice that that is comprised of pretty much that entire first group. The idea is that that first group, starting with Li, lithium to francium, are all alkali metals. Similarly, if we were to look at the next couple, let's look at transition metals right here in blue. That's this section right here in the middle. We also have different other types of names. We have halogens, Halogens, which is in light blue, that's that group 17 right there. We have noble gases, which are in purple. That's that group 18. So in some way, shape, or form, every element on this periodic table belongs to some group. It belongs to some ranking. It belongs to some classification. And within that classification, you can make predictions about elements. You can make statements about different types of elements. For example, metals. In general, we expect and see metals to be shiny, malleable, ductile, and good conductors. Notice I said metals in general. That applies to alkali metals, alkaline earth metals, transition metals, and other metals. We will not be going more specific, being able to describe, distinguish them, meaning we're not going to look at alkali versus alkaline versus transition, etc. Just metals in general. Then we have metalloids. Metalloids can be described as intermediates. Between metals and non-metals. What do I mean by that? Well, it means that metalloids generally may exhibit behavior of both metals and non-metals. I'm not going to necessarily say that metalloids generally take on I would say a gelatinous type structure. But looking at the metalloid scene here, it says metalloids are in gray. So that's over on this side right here. It's actually like a ladder. It's these guys right here. If you've ever worked with silicon, if you've ever seen silicon being deployed either in a computer chip or something else, you have an idea of what I mean by its consistency is a little gelatinous. It's not perfectly solid. It's not perfectly non-solid. It has properties of metals. It has properties of non-metals. It's right there smack dab in the middle. So then that begs the question, if that's metals, what about non-metals? All right, well, non-metals are presumably just going to be the polar opposite of metals. Where metals are shiny, non-metals are dull. While metals are malleable and ductile, non-metals are generally brittle. While metals are good conductors, non-metals are generally bad conductors. So this ranking system, this classification system, not only allows us to neatly organize the periodic table, but when we discover a new element, we can organize it appropriately. To be more specific, at number 104, Rutherfordium, from number 104 onward, so 104, 105, 106, 108, blah, 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 all the way to 118, those are all man-made elements. So I'll repeat myself. From 104 onward, so that is from Rutherford all the way to 118, all of these elements are man-made. Some of them share the name of either where they were discovered or who discovered them. We've talked about Rutherford a few times. Rutherford discovered Rutherfordium. He was able to put his name on it. I'm trying to think another one. MC Moscovium, that was actually discovered in Moscow. So sometimes just in the name of politeness, I guess, some people won't name it themselves, name it off of their own names. Maybe because it was a team effort, a research group's effort, they'll just name it after the school that it was founded at or the country. This was Moscovium. I think down here we'll also see, all right, BK as in Berkelium. Berkelium wasn't man-made, but it was discovered in Berkeley. Californium, discovered in Berkeley, in California. Einsteinium, well, Einstein discovered it, et cetera, et cetera. But 104 onward is man-made. So this is the benefit of the periodic table. It offers an organization system, it offers a classification system that allows us to make predictions, make educated guesses, and organize undiscovered elements. But it's not perfect. You see, the periodic table is above all else a theory. There are 118 elements. For every 10 elements that are perfectly ordered with their predictions, there's another 5 that are just like, oh yeah, it's in that same group, but it's not really in a lot in common. Meaning, just because we see nitrogen and phosphorus together in the same group, the same color, we don't expect them to be 100% match. Although they do share a lot of similarities, it's not perfect. So what I like to describe the periodic table as is a family. It has both siblings, cousins, second cousins. And although you may share a lot in common with your sibling and or your cousins, they're not perfect matches. So the one thing I want you to take away from all of what I'm saying right now is the periodic table is widely accepted as the perfect organization or classification system. But sometimes it's wrong, and that's okay. The simple truth is that no one has really been able to pitch a new periodic table that is much better than this. In fact, if you were to Google various periodic tables throughout history, some of them were triangles, like the food pyramid. Some of them were circles, like a staircase. There have been many people who had tried their own attempt at a periodic table. This is just the one that has stood the test of time. Now, we talk about all of these groups, these group 1, group 2, group 3, group 4, blah, 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 the periods and all that stuff. What exactly do those numbers tell us? I mean, is it really just a classification system, or is there some information we can glean? The answer is we can absolutely glean things. Groups tell us the amount of, and this is a new word, valence electrons. That word valence means outermost. Two ways to think about this. Taking a more planetary description, if we had a planet in the center and there are rings surrounding the planet, the valence electrons, the outermost electrons, are the ones located on the outermost ring. So the one farthest away from the center of the planet, the nucleus, the gooey chocolate center of the Ferrero Rocher. It should make sense to you physically that the rings will have some distance between them, and there will be one ring on the very far outsets. Another way to think about this is buildings. As buildings grow, the number of floors increase. If there was an alien invasion, if there was a meteor coming to Earth, who would get struck first? That top floor, the outermost shell, the outermost room, the outermost ring. That's why knowing the outermost electrons is useful. Because if just like the planetary system, just like this building, they're the first line of defense. They're the first line of barriers. So it is important for us to know how many valence electrons there are, because valence electrons actually do stuff. They're the ones that participate in reactions. They're the ones that react. They're the ones that will leave, that will enter. Such that we're able to say that the innermost electrons, aka the core electrons, are inert. Where inert means the same thing as unreactive. So what does this tell us? Well, it actually tells us a couple of things. Group number of valence electrons, here abbreviated as VE, valence electrons. Groups 1, 2, 3 to 12, 13, 14, 15, 16, 17, and 18. Group 1 has 1 valence electron. Group 2 has 2 valence electrons. Group 13, I'm purposefully skipping that 3 to 12 for right now. Group 13 has 3 valence electrons. 14 has 4 valence electrons. 15 has 5, 16 has 6, 17 has 7, 18 has 8. What about 3 to 12? Variable. Now, looking back at the periodic table, groups 3 to 12 is this center console right here. Following our key, these are transition metals. Transition metals display unique chemistry, and we will go into them in this class, but they're not as easy to just predict based off of group numbers. The best way I can tell you about this is CO as in cobalt. Cobalt, there is a blue cobalt. Oh, that's spelled wrong. There is a blue cobalt, cobalt blue. Probably you've heard of that color. It's a nice, rich blue. There's also the lesser known cobalt purple. And it might not seem like it, but these are 2 completely different kinds of cobalt. And you're not able to predict what you have solely because it's in group 9. You have to investigate a little further. So this is all to say that transition metal 3 to 12, they're a bit harder to predict. You'd have to look at them specifically. All right. That was groups. The columns, they tell us the amount of valence electrons. So what does periods tell us? Well, I've been frequently describing these atoms as planetary systems with rings around the planet. We've said that these rings are where the electrons are formed or found, sorry. Some planets have multiple rings. Periods indicates the amount of rings that orbit the nucleus. These rings are referred to as shells. And the period itself could be thought of as most analogous to a floor on a building plan. That is, as you add more periods, as you add more rings, aka shells, the atom gets bigger. Just as if you add more floors to a building, it gets taller. More periods / rings. The atom is overall larger. Does anyone have any questions so far? I just want to remind you once again, the periodic table in front of you will be part of your exam booklet, meaning I'll print a new one for each of you. So you're free to write up on this handout as much as you want, but I do expect you to continually carry this document back to class. Any questions? No? Okay. That leads us into our next topic under the periodic table. Ion formation. So we've talked about how on the periodic table, aka by default, whoops, spelled default wrong. By default, elements on the periodic table are neutral. What do I mean by that? Well, it has an equal number of electrons and protons. Don't forget, electrons are negatively charged, protons are positively charged. So when there's an equal number of positive and negative, it balances out, the molecule, the atom is overall neutral. However, neutral atoms can gain or lose electrons to form ions. Protons will never be gained nor lost. The only particle that is mobile are electrons. Does any brave soul want to take a guess why it's just electrons that are mobile? See your hand? Protons change the weight. Technically, electrons have a weight. So that argument isn't sufficient. Does anyone else want to try? Why is it electrons specifically? Think about where they're found. Think about that planetary system. See your hand. They're found on the outermost ring. I talked about that alien invasion analogy. It's the valence electrons that are our first line of defense. They're the ones that are going to get attacked. They're the ones that are going to do the attacking. And where is the protons located? In the nucleus, in that gooey chocolate center. That's the core of our planet, core of our system. We really would not want to mess with the core of a system or a planet if we can help it. Protons do not move. You have to have extreme equipment, extreme conditions. We're talking probably only in outer space. Electrons are the only ones that can move. So this begs the question, when an atom gains electrons, this is the shorthand for electrons, E with a dash above it like an apostrophe. I call it a God's comma. When an atom gains electrons, it is what's known as an anion. I like to think of the AN as a negative. In the situation that an atom loses electrons, it's called a cation. The way how I remember these, like I said, anion, a negative. And well, for me, cats have always been a positive experience. So anions are negatively charged overall. Cations are positively charged overall. Remember why? If you gain an electron, let me actually put some numbers to it. Let's look at a molecule such as B as in boron. Boron has an atomic number 5, has a mass, according to the periodic table, of 10.81. Well, all we really care about is the 5 for right now. When it's neutral, boron has 5 protons and 5 electrons. When it is B plus, it is still 5 protons, but it is 4 electrons. To become a cation, to become positive, you have to lose an electron. If this were negative, B minus, this would still be 5 protons, but instead be 6 electrons. Conventionally speaking, when it's just a situation where it's plus or negative 1, we don't really write the 1. That being said, if you wrote it, it's not that it would be wrong. It's just not conventionally written. So this is the fact that atoms, elements can gain or lose electrons. Why do they gain or lose electrons? Okay. We've talked about that they gain or lose. We've talked about the language we would use, cation, anion. We've talked about where the charge comes from. The big question, of course, is why would they gain or lose it in the first place? Well, the simple answer, whoops, because of group 18. If you look at your periodic table, group 18 is our noble gases. So just going back to the periodic table just to show you, group 18 was this column here in purple. Purple column, or the purple ones, are known as noble gases. Noble gases henceforth written as NGs, are royalty. They're the popular group at school. They're the Regina Georges and Mikes. Everybody wants to be like Mike. What makes Group 18 so popular? They have 8 valence electrons. Remember, valence electrons, those are the ones in the outermost shell. They're our first line of defense. We know how many there are from the group. Group 18 has 8. 17 has 7, 16 has 6, and so forth. Why do elements want to resemble noble gases? Because everybody wants 8 valence electrons. This is what's known as the octet rule. There is one exception to the octet rule. This is He as in helium. Take a look at your periodic table. Helium is the very first element in group 18. It's He, Michael Jackson's favorite element, he. Does anyone want to take a guess as to why helium specifically, and the big hint is to look at the table, why is helium an exception to the octet rule? See your hand? What's up? It's lighter. That is true. It's not the exact reason. You were looking at the mass. Is there another number? Yeah, what are you saying? It only has 2 electrons. If you look at the periodic table, helium has atomic number 2, which means that it only has 2 protons and 2 electrons. It's okay though. 2 is great. Helium is royalty. Helium is noble. 2 is okay with them. It's still called the octet rule, but 2 or 8 electrons are royalty. Two valence electrons. Okay. All right. So now we have a nice idea of why they gain or lose electrons. Looking at your periodic table, I'm looking at F, atom number 9, fluorine. Fluorine, I'll write it over here, normally has 9 electrons. If it gains an electrons, represented here as plus E, it becomes F minus. The minus, of course, is there to represent that there is an extra electron. In this state, the fluorine now has 10 electrons. Which noble gas has 10 electrons? Neon. So fluorine's happy. That's what fluorine wants. It wants to be like neon. Could it potentially be like argon? 18? Yeah, in theory. What if we just added nine electrons? Yeah, in theory, it would be F9 minus with 18 electrons. But do you think fluorine wants to put in all that work? Why would it? It's right there close to the neon. Why would it go to neon, join the group, the popular groups table, and then decide, you know what, I'm gonna keep going? So this now introduces another idea to nobility. Closeness. Oxygen, for example, there are two noble gases it is close to. It is close to neon to the right. It is close to helium. Let me draw that again, sorry. It is close to helium. Look at the size of those arrows. There is a noble gas that should be clearly the winner in terms of closeness. Neon. And looking at the number of electrons, just by show of hands with your pointer fingers, how many electrons does oxygen need to look like neon? See a couple peace symbols all the way around. Great, it just needs 2. Does that mean that it can't go back and form 2? I mean, in other words, we're saying right now oxygen normally has 8. It can gain 2 electrons to look like O2 minus. This is the closest one. This is great. But similarly speaking, you could lose 6 electrons to look like helium. Technically, it's still noble. But between you and I, which one do you think is the preferred nobility, the top or the bottom? The heart kind of gives it away. Oops. The top. So when it comes to identifying how many electrons and which direction gain or loss, it comes back to proximity. So let's now have a new table. Let me just copy this one back, actually. I'm going to erase the bottom. Whoops. Okay. Actually, you know what? Let me keep that valence stuff back because I purposefully want you to see how the numbers change. I actually want to keep that now that I think about it. We're going to put another line right through here. We're going to draw these down as best as we can. It's not perfect, but it'll have to work. Ideal charge, aka the charge of the group when thinking about its proximity. We've already talked about some of them so far. Group 17 just needs to gain 1 electron. So its ideal charge is -1. Remember, you gain an electron, you gain a negative particle, so you become negative. Why is that one the preferred? Well, technically, it could look like 2, but then it would have to lose 5 electrons. And at that point, it just becomes a numbers game. Group 7 would rather gain 1 electron than lose, was it 6? No. Helium is 2, fluorine, yeah, it would lose 7. It's just a numbers game at that point. Same thing for group 16. It can either gain 2 electrons or it can lose 6 electrons. Numbers game here. It'll prefer to gain, aka -2. Group 15 would rather gain 3 electrons, -3. Okay, what about from group 1? Now, Thinking about group one, let's use an actual element to help get our point across. Let's use lithium in group one. Lithium can either gain 7 electrons to look like neon, or it can lose 1 electron to look like helium. Numbers game. It's easier to lose 1 than gain 7. If we lose an electron, this becomes +1. Group 2, +2. Groups 3 to 12, variable. Remember, that's that transition metal area that I told you. It's a little complicated. You can't quite predict based off of columns. You have to investigate specifically. Group 3, 3+. What about group 4? Well, let's take a look at an actual element. Let's look at carbon. Carbon is close to neon and helium. Carbon can either gain 4 to look like neon, or it can lose 4 electrons. The number game isn't exactly going to help us here. Carbon is right on the borderline. Group 14 is right on the borderline. I am here today to tell you group 4 will always be +4. The only reason you need to understand is that it's easier to lose than gain. And since the numbers are exact, it would prefer to lose 4 electrons. What do you think is the ideal charge for noble gases? 0. They don't need to lose or gain anything. They're already noble. So why is noble gases so important? Well, they're royalty. Those 8 valence electrons are our first line of defense. That 8 is a magic number. In the case of helium, 2 is okay. Noble gases are incredibly stable. Helium you've used to blow up balloons. Neon lamps, argon gas lamps, neon lamps too, technically. Incredibly stable chemicals. In fact, there's a whole field of chemistry dedicated to studying these chemicals. And more often than not, they study them in outer space medium. Not meaning you go up to space and collect samples, but rather the astronauts bring samples back and you simulate outer space simulations, all that stuff. Do we have any questions? Okay. Next up, we're talking about periodic trends, and I'm actually going to get this periodic table again. Okay. I think what I am going to do is let's take this. Can I take a screen? No, I can't take a screenshot of just that piece, but that's okay. Then let's come here. I'm going to rotate this page. And then I can write all of my comments on this page with white space, not having to worry about all the other stuff. Okay. You got to love the iPad. All right. Now, under the realm of periodic table, we're talking about periodic trends. There are 3 primary effects that we are going to look at. Sorry, 4 actually. Number 1, we're going to look at atomic radius. Number 2, we're going to look at ionic radius. Number 3, we're going to look at ionization energy. And number 4, we're going to talk about electron affinity. Possible for me to duplicate? No, not export, not move. No, I can't duplicate the page, can I? Let me see if there's another option. Add page to outline? No. All right, that's okay. All right, the first one we're talking about. Let me just copy this thing so I can get it back. The first one we're going to talk about is atomic radius. Now, atomic radius has the following trend. Let me just get some, make some easier on myself. Oops. I just want to clear up some of that space so I can write in. Okay. Okay. As we move across the periodic table from left to right, atomic radius, AR, decreases. As we go down the periodic table, atomic radius increases. Let's talk about why that is. So going down the group, that one should be a little bit more intuitive. Remember, as we go down the group, we're actually going down periods. We've described periods as being those rings, those shells, the floors that you add to a building. As you go down a group, you add more floors, you add more shells. All of a sudden, your molecule just becomes bigger. Taking a look at the molecules up on the board, up on the projector. At the very top, we have lithium at 3 electrons. And then we have francium at 87 electrons. It should be fairly obvious that that will be much bigger because there are more floors, there are more shells. So going down the group, that's intuitive. That makes sense. What about going across the periodic table? That is from left to right. Why does it decrease? Because, I mean, technically by the same logic, if there are more electrons, shouldn't it be bigger? I mean, look at lithium, the third element, I'm sorry, I'm pointing to this TV in the back. Look at lithium, the third element, 3 electrons. And look at fluorine, number 9. In theory, shouldn't number 9 be bigger than number 3? This is more electrons. Well, remember, they're both in the same period. They're both in the same shell. They're both on the same floor of the building. So we're not really increasing the building's height. Okay, so using that analogy, why is it that more electrons on a shell is smaller? Think about that gooey chocolate center, the nucleus. The nucleus is positive, and the rings with the electrons are negative. As you increase electrons, you increase protons. So I want you to think about it like a bear hug, B-E-A-R hug. Lithium has 3 protons, 3 electrons. So its bear hug is, let's say, 3 times. Look at fluorine. Fluorine has 9 electrons, 9 protons. That's 3 times more. So its bear hug is even tighter. So going across the period from left to right, that hug gets tight. The hug between the nucleus and the rings. Why? Because of the attraction between positive and negative. They prefer to be much closer together. And then as you go down the group, you just increase floors, so the building gets taller. That's atomic radius. What about ionic radius? Ionic radius, on the other hand, actually does not have an explicit trend. What it does have instead is a statement that cations are smaller than their neutral counterparts, and anions are larger than their neutral counterpart. What does that mean? Well, take, for example, something like lithium, Li. When lithium loses an electron, it becomes smaller. When something like fluorine gains an electron, it becomes bigger. So there is no explicit trend with ionic radius. It simply depends on whether it's gaining or losing. All of this is to say, the more positive, the smaller. Okay. So that was the first two that we covered. Oops. Atomic radius and ionic radius. Next up is ionization energy. Ionization energy, whoops, can be described as the energy needed to lose electrons. Ionization energy is the energy needed to lose electrons. Going from left to right across the periodic table, ionization energy increases. Going down the periodic table, ionization energy decreases. And then finally, we're going to talk about electron affinity. Electron affinity, of course, the opposite of ionization, is the energy to gain an electron across the periodic table from left to right. Oops. EA, electron affinity, gets more negative, down the periodic table, it's actually less predictable. So there isn't an explicit trend going down the periodic table. Don't worry if these trends aren't clicking in right immediately. We have a workshop today in 15 minutes focused on today's topic. For right now, does anyone have any questions? Yeah.
What do you mean by it's more effective?
We're going to talk a little bit about some other examples now. We're just running out of time.
Fair enough.
All right. It is 1:15. We will end the lecture for today. We'll take a 15-minute break and we'll do today's workshop right in here. I'll see you all in about 15 minutes.